Welcome to this coding problem walkthrough. In this session, we will be exploring problem number 950, reveal cards in increasing order. This problem challenges us to determine an efficient way to simulate and reveal cards in a specific order while maintaining constraints. Let's dive in and uncover the best approach to solve it. In this problem, we are given a deck of cards represented as an integer array called deck. Each card in the deck has a unique integer value, and importantly, the deck is not sorted. The task is to arrange the cards in such a way that they can be revealed in a specific sequence. Here's how the process works. First, the top card of the deck is revealed and removed. If there are still cards left, the next card is moved to the bottom of the deck. These two steps are repeated until no cards remain. The challenge is to return an ordering of the deck such that, when the cards are revealed following these steps, they appear in increasing order. The input is the unsorted array deck, and the output is the rearranged array that satisfies this condition. To better understand the problem, let's look at an example. Suppose the input deck is 17, 13, 11, 2, 3, 5, 7. If we reorder the deck as 2, 13, 3, 11, 5, 17, 7, the cards will be revealed in increasing order. Here's the sequence. First, 2 is revealed, leaving 13, 3, 11, 5, 17, 7. Next, 13 is moved to the bottom, resulting in 3, 11, 5, 17, 7, 13. Then, 3 is revealed, leaving 11, 5, 17, 7, 13. The process continues by moving 11 to the bottom and revealing 5. This sequence of revealing and rearranging continues until all cards are revealed. The process for the first example continues like this. After revealing 5, 17 is moved to the bottom, and 7 is revealed. Then 13 is moved to the bottom, and 11 is revealed. Following this, 17 is moved to the bottom again, and 13 is revealed. Finally, the last card, 17, is revealed. At the end of this process, the reveal sequence is 2, 13, 3, 11, 5, 17, 7, which matches the desired increasing order. Now, let's consider another example to further clarify the problem. In the second example, the input deck is 1, 4, 7, 3. If we reorder the deck as 1, 7, 3, 4, the cards are revealed in this sequence. First, 1 is revealed, leaving 7, 3, 4. Then 7 is moved to the bottom, and 3 is revealed, leaving 4, 7. Next, 4 is moved to the bottom, and 7 is revealed. Finally, the last card, 4, is revealed. The resulting reveal sequence is 1, 7, 3, 4. This example demonstrates that different input decks will require different reorderings to achieve the desired sequence. Let's also take a look at some constraints and edge cases to keep in mind while solving the problem. When solving this problem, there are a few important considerations. First, for small deck sizes, the solution should handle cases like deck equals 1, where the output is 1, since there's only one card, or deck equals 5, 10, which already satisfies the reveal sequence. For larger inputs, the solution must remain efficient as the deck size approaches 1,000 cards. Additionally, the solution needs to handle edge values where card numbers are very large, up to 10 to the power of 6. Finally, since the input deck is unsorted, the algorithm should sort the deck before constructing the reveal sequence, ensuring the output meets the required increasing order. To begin solving this problem, we first considered a brute force approach that directly simulates the card revealing process step by step. The intuition here is straightforward. Start with the deck sorted in ascending order and use a queue to manage the indices of the deck. At each step, we place the smallest available card into the position indicated by the front of the queue. After that, we simulate the rotation described in the problem by moving the next index from the front to the back of the queue. This process continues until all cards are placed in their correct positions. The steps include sorting the deck, initializing the queue with natural indices, and iterating through the sorted deck while applying the placement and rotation rules. While this approach is efficient in terms of time complexity, n log n, due to the sorting step, it can be less intuitive, as the queue manipulation requires careful handling to align with the problem's requirements. An alternative approach to solving this problem is to reverse the simulation process. Instead of simulating forward, we can work backward using a process that starts with the largest card and reconstructs the deck in reverse order. The idea is to place the largest card at the front of the resulting array and then simulate the rotation by moving the bottommost card to the top, if any cards already exist in the result. To implement this, we first sort the deck in ascending order, then iterate through the cards in reverse, from largest to smallest. For each card, if the result array is non-empty, we rotate the last card to the front before placing the current card at the front. This reverse simulation eliminates the need for explicit queue operations and simplifies the implementation. It also achieves the same optimal time complexity of O, n log n. The reverse simulation approach is not only simpler to implement but also easier to understand conceptually. By avoiding explicit queue manipulation, it streamlines the logic while maintaining the same level of efficiency. However, this method does require some additional intuition to recognize that reconstructing the deck in reverse achieves the same order as simulating the forward process. After evaluating both approaches, we chose the reverse simulation strategy for three main reasons. First, it achieves the optimal time complexity of O, n log n. Second, it's easier to implement, as it avoids the need for managing a queue explicitly. Finally, the reverse process provides a clear, iterative way to construct the result. Through careful observation, we noted that sorting the deck is a necessary step in both approaches, and while the brute force method aligns more directly with the problem statement, the reverse method offers a more streamlined solution. While the brute force simulation has the advantage of being conceptually aligned with the problem, managing the queue can make it less intuitive to implement. In contrast, the reverse simulation, though slightly less direct, simplifies the implementation while maintaining the same time complexity. Now, let's look at the final algorithm for the reverse simulation approach. The implementation begins by sorting the deck in descending order. We use a deque to store the result, which allows us to efficiently manipulate the front and back of the sequence. For each card in the sorted deck, we first rotate the last card to the front, but only if the result is non-empty. Then, we place the current largest card at the front of the deque. Once all cards have been processed, the deque is converted to a list and returned. This ensures the result adheres to the problem's constraints while being efficient and straightforward to implement. The final algorithm efficiently reconstructs the deck in the desired order by reversing the card reveal process. First, we sort the deck in descending order, which ensures that we handle the largest cards first. Using a deque, we iterate through the sorted cards, rotating the last card to the front if the result is non-empty and then placing the current card at the front. This process is repeated until all cards are placed in the correct positions. The resulting deque is then converted to a list and returned as the final output. This approach is both intuitive and adheres to the problem constraints, providing a clean and efficient solution to the problem of revealing cards in increasing order. In this problem, our goal is to determine the original order of a deck of cards that would produce a specific reveal sequence. The sequence follows a pattern where the smallest card is revealed first, and every subsequent card is revealed in increasing order. An important step here is that after revealing a card, the next card in the deck is placed at the bottom before moving on to the next reveal. To solve this, we will reverse engineer the process by determining the positions where each card should be placed. First, we start by sorting the deck in ascending order. This is because the smallest card must be the first to be revealed, and sorting ensures the correct order for placement. For instance, if the deck is 17, 13, 11, 2, 3, 5, 7, sorting it gives 2, 3, 5, 7, 11, 13, 17. Next, we initialize a queue containing the indices of the deck. These indices will represent the positions where each card will eventually be placed. For a deck of size 7, the queue would be 0, 1, 2, 3, 4, 5, 6. Using indices allows us to simulate the reveal process without directly modifying the deck, keeping our operations efficient and organized. Now, we proceed to place the cards in the correct order using the queue. For each card in the sorted deck, we pop the front index from the queue and place the card at that position in the result array. After placing the card, if the queue is not empty, we take the next index at the front of the queue and move it to the back. This step mimics the action of rotating the deck to the bottom after each reveal. Let's go through an example. Starting with the sorted deck 2, 3, 5, 7, 11, 13, 17, and the queue 0, 1, 2, 3, 4, 5, 6, we place 2 at index 0, and the queue becomes 1, 2, 3, 4, 5, 6. Then, we move index 1 to the back, resulting in 2, 3, 4, 5, 6, 1. Next, we place 3 at index 2. The queue is now 3, 4, 5, 6, 1. We repeat this process for all cards, ensuring each is placed in its correct position. By the end, all cards are placed, and the result array represents the original deck order. For example, the result array 2, 13, 3, 11, 5, 17, 7 corresponds to the desired reveal sequence. This approach is built on several key insights. First, sorting the deck guarantees that the smallest card is placed first, which aligns with the reveal order. The use of a queue is crucial as it efficiently simulates the process of rotating the deck to the back after each reveal step. Each card is placed exactly once, and queue operations like removing the front or adding to the back are performed in constant time. Combining this with the sorting step, the overall time complexity of the algorithm is O, n log n. The space complexity is O, n, as we use both a queue and a result array of size n. The algorithm handles edge cases seamlessly. For an empty deck, we return an empty array. For a single card, the card itself is the result. If the deck is already sorted, no additional handling is required as the algorithm naturally works for such inputs. Overall, this method combines sorting, queue mechanics, and direct indexing to efficiently reconstruct the original deck order. This implementation solves the problem reveal cards in increasing order by simulating the process outlined in the problem description. Here's a detailed explanation of the solution. 1. Sorting the deck. The deck is sorted in ascending order using deck.sort. This ensures that we process cards from the smallest to the largest, as required by the problem. 2. Using a deque. A deque, double-ended queue, is used to maintain the indices of the result array. We initialize it with indices from 0 to n1. This deque helps us simulate the reveal order efficiently. 3. Result array. An array result of size n is initialized with zeros. This array will hold the final arrangement of the deck. For simulating the reveal process, for each card in the sorted deck, the smallest card is placed at the index obtained by popping from the front of the deque. If the deque is not empty, the next index is moved from the front to the back of the deque to simulate the process of skipping one position. 5. Returning the result. After all cards are placed, the result array contains the deck in the required order, which is returned. This approach is efficient, with a time complexity of O, n log n, due to sorting, and the deque operations are performed in O, n. The solution handles edge cases such as a single card or an already ordered deck seamlessly. Here, we start by importing the necessary packages and defining a public class called solution with the method deckRevealedIncreasing. The first step inside this method is to sort the input array, deck, in ascending order using arrays.sort. This ensures that we handle the cards in the correct sequence, starting from the smallest value. Next, we initialize a queue, index queue, to simulate the process of revealing cards. The queue is populated with indices from 0 to n1, where n is the length of the deck. This queue will help us manage the order in which cards are placed in the result array. Finally, we declare an empty result array of the same length as the input deck, which will store the final order of the cards. In the next part of the code, we iterate through each card in the sorted deck. For every card, we take the first available index from the queue, using the pull method, and place the card at that index in the result array. Then, to simulate the process of moving the next index to the back of the queue, we check if the queue is not empty. If it's not, we pull the next index and add it back to the end of the queue. This ensures the proper sequence of revealing cards, as per the rules of the problem. Once all cards have been placed in the result array, we return it as the output. This approach efficiently replicates the reveal process while maintaining the desired order. To solve this problem, we start by considering a deck of cards given as 17, 13, 11, 2, 3, 5, 7. The process begins with sorting the deck in ascending order, resulting in 2, 3, 5, 7, 11, 13, 17. This ensures the cards are arranged in increasing order of value. Next, we initialize two data structures, an index_q to manage the positions where cards will be placed, starting with all indices of the deck, and an empty result array to hold the final arrangement of the cards. The index_q begins as dec 0, 1, 2, 3, 4, 5, 6, and the result array is initialized as 0, 0, 0, 0, 0, 0, 0. The goal is to simulate the process of revealing cards while preserving the specified order. For each card in the sorted deck, we will place it at the front index of index_q and adjust the queue to mimic the reveal process. We now begin placing cards into the result array step by step. First, the smallest card, 2, is placed at index 0, the front of index_q. This updates the result array to 2, 0, 0, 0, 0, 0, 0, and index_q becomes dec 1, 2, 3, 4, 5, 6. To simulate the next card reveal, we move index 1 to the back of the queue, resulting in dec 2, 3, 4, 5, 6, 1. Next, card 3 is placed at index 2, updating the result array to 2, 0, 3, 0, 0, 0, 0. The index_q becomes dec 3, 4, 5, 6, 1, and then index 3 is moved to the back, resulting in dec 4, 5, 6, 1, 3. Similarly, card 5 is placed at index 4, updating the result array to 2, 0, 3, 0, 5, 0, 0. Afterward, index_q updates to dec 5, 6, 1, 3, and index 5 is moved to the back, making index_q dec 6, 1, 3, 5. The process continues with card 7, which is placed at index 6, updating the result array to 2, 0, 3, 0, 5, 0, 7. The index_q becomes dec 1, 3, 5, and index 1 is moved to the back, resulting in dec 3, 5, 1. Next, card 11 is placed at index 3, updating the result array to 2, 0, 3, 11, 5, 0, 7. The index_q updates to dec 5, 1, and index 5 is moved to the back, making index_q dec 1, 5. Then, card 13 is placed at index 1, updating the result array to 2, 13, 3, 11, 5, 0, 7. At this point, index_q becomes dec 5, and moving index 5 to the back doesn't change the queue since it contains only one element. Finally, card 17, the largest card, is placed at index 5, which is the last remaining position in index_q. This updates the result array to 2, 13, 3, 11, 5, 17, 7, and index_q becomes empty, signaling that all cards have been placed. The final result for this example is 2, 13, 3, 11, 5, 17, 7. A second example starts with the deck 1, 100, 50, 25. First, we sort the deck in ascending order, resulting in 1, 25, 50, 100. With the deck sorted as 1, 25, 50, 100, we initialize the index_q to dec 0, 1, 2, 3, and the result array to 0, 0, 0, 0. For the first iteration, card 1 is placed at index 0, updating the result array to 1, 0, 0, 0. The index_q becomes dec 1, 2, 3, and index 1 is moved to the back, resulting in dec 2, 3, 1. In the second iteration, card 25 is placed at index 2, updating the result array to 1, 0, 25, 0. The index_q updates to dec 3, 1, and moving index 3 to the back makes index_q dec 1, 3. Next, card 50 is placed at index 1, updating the result array to 1, 50, 25, 0. The index_q becomes dec 3. Finally, the largest card, 100, is placed at index 3, updating the result array to 1, 50, 25, 100. With index_q now empty, the process is complete, and the final result for this example is 1, 50, 25, 100. In the third example, the deck is 4, 8, 6. Sorting this deck results in 4, 6, 8. For the deck 4, 6, 8, we initialize index_q as dec 0, 1, 2, and result as 0, 0, 0. In the first iteration, card 4 is placed at index 0, updating the result array to 4, 0, 0. The index_q becomes dec 1, 2, and index 1 is moved to the back, resulting in dec 2, 1. In the second iteration, card 6 is placed at index 2, updating the result array to 4, 0, 6. The index underscore q becomes dec 1. Finally, card 8 is placed at index 1, updating the result array to 4, 8, 6. With index underscore q now empty, the process is complete, and the final result for this example is 4, 8, 6. The algorithm works by sorting the deck and simulating the card reveal process using a dec to manage indices. This ensures cards are placed in the correct order while mimicking the step-by-step reveal. Each iteration handles the smallest remaining card, placing it in the appropriate position and rearranging the dec to match the reveal process. This approach guarantees that the cards are revealed in strictly increasing order, resulting in the desired final arrangement. In this problem, the time complexity is determined by the key steps of the solution. First, we sort the deck of cards in ascending order using the deck.sort method. Sorting involves rearranging all n elements in the deck, which takes n log n time. After that, we initialize a dec with indices ranging from 0 to n1 using the dec range n operation. This step requires iterating over all n indices, which contributes an additional n to the time complexity. These two steps set the foundation for the rest of the algorithm. The next step is simulating the reveal process. Here, the algorithm processes each of the n cards in the sorted deck. For every card, the smallest available index is removed from the front of the dec using the popleft operation, which is an O1 operation. If the dec still contains indices, the next available index is moved to the back of the dec using append, popleft, a combination of two O1 operations. Since these operations are performed for each of the n cards, this step contributes n to the total time complexity. Finally, each card is placed in the result array, where each placement is a simple O1 operation, repeated n times, adding another n. Combining all these steps, the dominant term remains the sorting step, so the total time complexity is n log n. Now, let's analyze the space complexity of the solution. The first primary contributor to space usage is the result array, which has a size of n, contributing n space. Next, we have the dec, which is used to store indices from 0 to n1. At any given time, it contains up to n indices, so it also contributes n space. The input deck itself does not require additional memory during sorting, as the sorting is done in place. Therefore, the memory usage for the input deck is also n. These components together determine the space complexity of the solution. When we combine all space usage, the total space complexity comes from the result array and the dec, both of which are of size n. This gives us n plus n plus n, which simplifies to n. Importantly, this space complexity remains consistent across all cases best, worst, and average since the algorithm does not allocate additional memory based on input order or size. Similarly, the time complexity remains n log n for all cases as sorting and the simulation steps are deterministic and do not depend on the specific arrangement of the input deck. To compare with a naive approach, a brute force solution would involve repeatedly finding the smallest card and simulating the reveal process for each card. This would require not just sorting, but also nested iterations to simulate the reveal process, leading to a much higher time complexity of n squared. The space complexity for this naive approach remains n, due to the result array and any intermediate data structures. In contrast, the optimized solution achieves a significant improvement in time complexity by reducing it to n log n, through an efficient combination of sorting and dec operations, while maintaining the same optimal space complexity of n. Finally, let's validate the big O analysis mathematically. For time complexity, sorting the deck contributes n log n. The simulation process, which involves n iterations of O1 operations, adds n. Adding these together results in n log n plus n, which simplifies to n log n. For space complexity, the result array and the dec each require n space, resulting in a total of n. These calculations confirm that the solution is efficient both in terms of time and memory usage, making it the optimal approach for this problem. When tackling this problem, it's important to avoid a few common mistakes. First, not sorting the deck before simulating the process is a frequent error. The problem requires that the cards are revealed in an order that produces a sorted sequence, so skipping this step will almost always lead to incorrect results. Next, be cautious with queue operations. The reveal and move to the bottom process must be simulated accurately. For example, using queue.pop instead of queue.popleft can completely change the order, leading to misplaced indices. Another pitfall is relying on a brute force approach. While trying all permutations might seem like an option, this has a time complexity of O(n), which is impractical for larger decks. Lastly, always pay attention to the problem constraints. Misinterpreting details like the guaranteed distinct card values or the range of card numbers can add unnecessary complexity or cause outright errors in your solution. Off-by-one errors are another common issue, especially when managing indices or shifting positions in the queue. This often happens with zero-based indexing, so being meticulous about the position calculations is essential. From an interview perspective, this problem is a great opportunity to demonstrate pattern recognition. Many similar problems involve simulating processes with queues or stacks, so recognizing that sorting followed by a structured simulation is key can give you a major advantage. Additionally, this problem tests your ability to reconstruct an order based on constraints, so focus on the interplay between the sorted input and the desired output. It's also a chance to showcase your familiarity with auxiliary data structures like queues and deques, which are particularly efficient for simulations like this. Finally, be prepared to discuss time complexity. Highlighting why an O(n) log n solution is more optimal than a brute force O(n) approach shows a strong command of algorithmic efficiency. This problem is closely tied to several related problems that can help deepen your understanding of similar concepts. For example, LeetCode 621, Task Scheduler, involves a scheduling problem with constraints and makes use of queues. LeetCode 239, Sliding Window Maximum, is another excellent example, as it requires efficient use of deques to maintain order within a sliding window. LeetCode 862, Shortest Subarray with Sum at least k, also relies on careful deque operations to manage constraints effectively. And, of course, there's the problem itself, LeetCode 950, which serves as a direct application of these techniques. Exploring these related problems can help you build a toolkit of strategies for handling queue-based simulations and constrained orderings in various contexts. There are several approaches to solving this problem, each with its own trade-offs. The most efficient is the simulation approach, which combines sorting with a queue. With a time complexity of O(n) log n, this method involves sorting the deck first and then using a queue to simulate the reveal process step by step. This aligns perfectly with the problem requirements. Another option, though less practical, is recursive backtracking. This involves generating all possible permutations and checking each one for correctness. While this brute force approach may work for very small inputs, its O(n) time complexity makes it infeasible for larger decks. Lastly, some edge cases may allow for a greedy approach, where you directly construct the result using a specific heuristic, such as placing the largest value at the end. However, this method isn't generally applicable and should be used with caution. By understanding these approaches, you can select the most appropriate strategy based on the problem constraints and input size. Great job! To summarize, we tackled the reveal cards in increasing order problem by leveraging a deque for efficient simulation. We also highlighted the importance of sorting in sequential problems. Remember to practice similar problems to enhance your skills. Thanks for joining, and see you in the next walkthrough. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!